We're now ready to prove the first major limit theorem of probability theory, the strong law of large numbers. Now, remember back from lecture 12.2 where we stated and proved a weak law of large numbers. That regarded a sequence of uncorrelated random variables. Remember that uncorrelated means that any two random variables in the sequence, not equal to each other, have covariance 0. In order for that to make sense, all of those random variables have to be in L2. Covariance is just the L2 inner product of the centered versions of the random variables. That weak law of large numbers was the statement that if xn is a sequence of uncorrelated random variables, all with common expected value alpha and common variance s squared, that is finite, then the empirical average, the sum of the first n divided by n, converges in probability to that common mean, alpha. In fact, we proved something a little bit more. We proved that the convergence rate in probability was 1 over n at worst. That is, the probability that Sn over n minus alpha exceeds epsilon was less than or equal to the variance divided by epsilon squared times 1 over n. And that, in fact, is generally sharp. The proof of this limit theorem was a simple one-line application of Chebyshev's inequality. As a result, we might expect that it's just not the best theorem that we could prove, and there are at least two shortcomings of it. Primarily, it's the notion of convergence. We only proved convergence in probability. Now, we know that convergence in probability implies almost sure convergence of a subsequence. So we can conclude from here that this sequence of empirical averages does have a subsequence that converges almost surely to the common mean alpha. But that could mean that there are arbitrarily large n for which there's a positive probability that this thing is not concentrated near alpha. As a matter of practice, that's not what happens. It just means that we have to work harder to prove it. At the same time, notice that the theorem is about averages and expected values. But in order to apply Chebyshev's inequality, and in fact even state the condition of being uncorrelated, we needed to assume the random variables were in L2. It would be more natural if we could replace this L2 assumption with xn simply being in L1. So that's what we'd like to do. Weaken the conditions, being in L2 to being in the more natural L1, and strengthen the convergence from convergence in probability to convergence almost surely. Now, in this lecture, we're going to discuss the main workhorse technique, at least for point 1, which is to do a cutoff argument. This is a technique that's going to work for us in a lot of different contexts in the future. The idea is to take random variables that aren't as integrable as we need for a proof we know how to work, and cut them off in some way to make the new versions in that space, prove the theorem we want, and then carefully remove the cutoff after the fact, hopefully preserving the result. Let's look at some detail. Let x be any random variable. We'll make no integrability assumptions at all, and let m be some positive finite constant. Then we can cut off x by m as follows. We just take a new random variable which takes the same values of x as long as x doesn't exceed m in absolute value, but is 0 whenever x is larger than m in absolute value. Now, by construction, this random variable is always less than or equal to the constant m, and therefore it is bounded, which means it is in LP for every p, in particular L2, which is what we'll need for the law of large numbers. To see that, just note that the cutoff is less than or equal to m, therefore the pth power is less than or equal to the pth power of m, and therefore the expected value of that is less than or equal to the expected value of m to the p, which is just m to the p, which is finite. On the other hand, this new random variable, the cutoff x, is still measurable with respect to the sigma field generated by x. And the reason for that is that the cutoff can be written as a nice function of x. That function is just the cutoff function, x times the indicator that the real number x is less than or equal to m. In other words, it's the identity function on the interval from minus m up to m and 0 outside that interval. That is, of course, a Borel measurable function, which means that its composition with x, which is the desired cutoff, is still measurable with respect to the sigma field generated by x. Great, we've replaced an arbitrary random variable with one equivalently measurable that is bounded and therefore in L2. The trouble is that this process does not preserve uncorrelatedness. Uncorrelated random variables are those that have covariance 0, but there's no reason to think that functions of uncorrelated random variables are uncorrelated. In general, they are not. So the solution to that is to trade up. The theorem is not going to be about uncorrelated random variables. It's going to be about the stronger assumption of independent random variables. Remember, independence implies uncorrelated if the variables are in L2. But the nice fact is that independence makes sense for any random variables, regardless of how integrable they are. Now, a sequence of random variables is independent if and only if the sequence of sigma fields that they generate is an independent family of sigma fields. And thus, doing these cutoffs, since they remain measurable with respect to those sigma fields, we see that the sequence of cutoff random variables, even if we cut off by different cutoff heights, is an independent sequence. So that's going to be our approach. We'll start with a sequence of independent L1 random variables, and then we'll do a cutoff to make the new cutoff random variables in L2. We'll use some L2 theory in order to prove the result that we want about their empirical average converging almost surely, and then we'll justify removing the cutoff after the fact, carefully. So before we get into those details, let's now state the theorem. This is Kolmogorov's strong law of large numbers. If xn is a sequence of IID L1 random variables with common mean alpha, then their empirical average, the sum of the first n divided by n, converges to alpha almost surely. Now, once we've proved that, we can also easily see that the L1 assumption is necessary. For suppose that xn is not in L1. We'd like to model the situation where the expected value is infinity. But xn isn't necessarily a positive random variable, so we don't even know how to take the expected value of xn. But there is a sense in which this could be true. That is, let's assume that xn is not in L1, but that its negative part is in L1, so that the blow-up of the L1 norm all comes from the positive part. Then it's fair to say that the expected value of xn, which should be the infinite expected value of the positive part minus the finite expected value of the negative part, is plus infinity. Under this assumption, it follows from the strong law of large numbers that the empirical average does converge, or diverge, depending on your preferred notation, to plus infinity with probability 1. And to prove that, we'll do a different sort of replacement, not a cutoff, but a minimum function. Let's fix a height m, finite positive number, and let xnm be the minimum of xn and m. Now, importantly, this is not cutting off the values of xn when they're negative. It's only when xn gets too big in the positive direction that we say, stop at height m. We're not making xn 0 when it actually exceeds m. We're making it always equal to m whenever it exceeds that cutoff m. Now, just like with the cutoff, these are now bounded random variables above. And therefore, since the negative part is in L1, these random variables are in L1. They're also independent for the same reason that the cutoffs were independent. This random variable is measurable with respect to the sigma field generated by xn, and they are identically distributed because they're all the same function applied to each xn, which were identically distributed. Therefore, by Kolmogorov's strong law of large numbers, we can conclude that SNM over n, which is the sum of the first n x and m's, does converge almost surely to the expected value of, say, x1m. Now here's the deal. Because we did a minimum with a height m instead of a cutoff, xn minimum with m is actually always less than or equal to xn. And so that means that Sn over n, the actual full sum, is bigger than or equal to Snm over n. And therefore, the lim_inf of that empirical average is bigger than or equal to the lim_inf of the minimized average. But that lim_inf is the limit almost surely. So that gives us the expected value of x1 minimized with m. Now what is that expected value? It's the expected value of the positive part minus the expected value of the negative part. Replacing x1 with m when it gets over m in height doesn't change the negative part. And so this is just the negative part of x, which gives us finite expectation for that term by assumption. On the other hand, it's also easy to check that the positive part of x1 minimized with m is the positive part of x1 minimized with m. Now, as we let m grow to infinity, this is a non-decreasing sequence of functions. And therefore, by the monotone convergence theorem, the expected value here converges to the integral of x1 plus, which we assumed to be infinity. And therefore, this term goes off to infinity, which concludes the proof of the result. All right, so our goal for the next 3 lectures is to prove this strong law of large numbers. And as we alluded to, the method we're going to use to start that proof is to replace the IID xn's that are only in L1 with cutoffs that are bounded, and in particular in L2. In order to do that, we need to cut them off in such a way that the new ones have the same tail behavior as the old ones in order to recover this tail result. And so that brings us to the notion of tail equivalence. 2 sequences of random variables are called tail equivalent if the sum over all n of the probability that the nth in the first sequence differs from the nth in the second sequence is a finite sum. Why is this our specific notion of tail equivalence? Because of the Borel-Cantelli lemma, part 1, that doesn't have any independence assumptions actually. If this condition holds, then consider the event that xn and xn prime differ. By assumption, the sum of the probabilities of an is finite, and therefore by the Borel-Cantelli lemma, the probability that the event an occurs for infinitely many n is 0. In other words, there is a null set n such that for all outcomes outside that null set, xn of that outcome agrees with xn prime of that outcome for all but finitely many n. Now notice that the finite set of n's for which these are allowed to disagree depends on the outcome omega. There's no uniform statement here, but that's okay. We don't need it to be uniform. For each realization of these random variables, these agree eventually. That is a nice intuitive interpretation of what tail equivalence should mean, but it's summarized in this nice, easily checkable format. One nice feature of this is that it works very well with the kind of theorem we want to prove. We'd like to prove something about empirical averages, which means we're taking a sum of n terms and dividing by n. Well, generally speaking, if I have 2 sequences that are tail equivalent, and if I have a renormalizing sequence of real numbers, Bn, that diverges to infinity, then if the renormalized sum of the first n of one of the sequences does converge to some random variable, almost surely, then the same renormalized sum of that sequence will converge almost surely to the same random variable. And the reason for that is the same observation we've made several times in the previous lectures, which is that this limit, because Bn goes to infinity, is equal to the limit, as n goes to infinity, of 1 over Bn times the sum j going from capital M up to n of xj for any m. And that's just because the sum of the first m minus 1 terms here divided by Bn goes to 0 as n goes to infinity for fixed n. But we can then choose m large enough that xj is equal to xj prime beyond m. And therefore, we get the same limiting sum as over here. So what we'd like to do is choose a sequence of cutoffs for our IID random variables so that the new cutoff sequence of random variables is tail equivalent to the original sequence. It turns out we don't have to work very hard to make that work. The result is that if I cut off the nth random variable by n, then that new sequence is tail equivalent to the old one. And that follows from the following simple lemma, which is a strengthening of Markov's inequality. If I take any L1 random variable and any tolerance epsilon, and I look at the probability that the absolute value of x exceeds n times epsilon and sum that up over all n's, that's actually finite. It's bounded by 1 over epsilon times the L1 norm of x. Now compare that to Markov's inequality. Markov's inequality would say for any one term in this sum, that the probability that x is bigger than or equal to n times epsilon is less than or equal to 1 over n epsilon times the expected value of the absolute value of x. And so in order to say something about the sum, if I try to take the sum over all n of this, what I'll get is that's less than or equal to the sum of the right-hand side, but the sum of 1 over n diverges, and so this gives us no information. Nevertheless, it turns out that this sum is actually bounded by the same thing that Markov would bound only the first term by. And to see that, we just look at the following step function. This is the function that takes x to the following sum, the sum of the indicator of the interval from n up to infinity at x. In other words, if x is less than 1, this is the sum of no terms. If x is between 1 and 2, it's the sum of this one term. If x is between 2 and 3, it's the sum of these two terms, and so on up this staircase. Now from the picture, it's clear that this function is less than or equal to x for all positive x. So what we're going to do is evaluate that inequality where we take x to equal the absolute value of our random variable divided by epsilon. Now note that this indicator function here is the same as the indicator of the set where x over epsilon in absolute value is bigger than or equal to n. In other words, it's the indicator of the set where absolute value of x is bigger than or equal to n times epsilon. And so if I just take the expected value of both sides of this, that gives me the expected value here, which is equal to that probability, proving the lemma. And therefore, we can see that doing the cutoff of xn by n in any identically distributed sequence will give a new tail equivalent sequence. The reason is just the calculation. If I sum n up to infinity of the probability that this cutoff xn prime does not equal xn, how can xn fail to equal xn prime, where this is xn prime? They only fail to be the same when the absolute value of xn is bigger than n. And so this is the same thing as the sum of the probability that the absolute value of xn is bigger than n. Now, this probability is a function of the distribution of xn, but our assumption is that the xn are all identically distributed. So we can replace xn by x1 there. But now we can just apply the lemma in the case where epsilon equals 1 and see that this is bounded by the expected value of the absolute value of x1, which we assumed to be finite. And therefore, by definition, the new sequence xn prime of cutoff random variables is tail equivalent to the old one. So that's going to be our method going forward. In order to prove the strong law of large numbers, it will suffice starting with an IID sequence of L1 random variables to replace them with cutoff random variables, where we replace the kth random variable with the cutoff at height k. Then all we need to show is that that cutoff sum has empirical average, which converges to the common mean of the original xn's almost surely. The advantage of this approach is that we have replaced all of the original random variables that are only assumed to be in L1 with bounded random variables, which are therefore in L2, and we can use L2 methods in order to prove the convergence. The disadvantage is we've given something up. The original random variables were independent and identically distributed. The new random variables, which are cutoffs of the old ones, are still independent. That's crucial here. But they are not identically distributed. That's going to create some headaches for us. However, they are asymptotically identically distributed. For large K, this cutoff shouldn't affect the distribution very much, since being L1 random variables by Markov's inequality, there is at least a polynomial decay in the tails of the random variables. Now, we're not going to use those kind of calculations directly, but it is good to keep them in mind for intuition as we develop the precise tools we'll need to prove this theorem. Those tools, which will be the topic of the next lecture, are all named after Kolmogorov.